A new study warns that the Taurid meteor stream could pose a serious risk to planet Earth. The Taurids are generated as the Earth passes through the debris stream created by the comet 2P Encke, which itself could be a piece of a larger comet that broke apart eons ago, creating a pile of debris that's being held in its orbit by Jupiter's gravity. The Earth passes through this stream twice every year, once in June, then again in October. Included in this stream is a denser cluster of gravelly meteoroids called the Taurid swarm, thought to be a massive ribbon of rock some 75 million by 150 million kilometres across. When it comes to the most likely extinction-level events for planet Earth, astronomers usually look at two primary threats: long-period comets from the outer solar system and NEOs, or near-Earth objects, like asteroids and meteoroids. Over the past few decades, astronomers have spent a great deal of effort trying to find, catalogue and study these primary celestial threats. Scientists think they've probably detected about 90% of the really big, potentially dangerous NEOs, and are now working hard to try and find the rest. But now, a report in the monthly notices of the Royal Astronomical Society and on the pre-press physics website archive.org claims the Taurid swarm is a third potential source of risk, one which the authors say changes the probabilities of potential catastrophic impacts. New calculations suggest the famous Tunguska asteroid impact may well have been caused by a Taurid swarm meteoroid. The famous event occurred on June the 30th, 1908, when an object about 100 meters wide airburst in the skies above the Siberian Tunguska region in Russia. The event still haunts scientists today because of the utter devastation it caused, literally flattening 2,000 square kilometers of forests into matchsticks. The blast was so bright, it lit up the night sky in London, a third of the way around the planet, with local Londoners able to read the evening newspapers without the need of artificial lighting. Tunguska remains the largest known Earth impact event in recorded history. Astronomers considered it a 1 in 1,000 year event, assuming a random distribution of events over time. But the authors of this study say their work on the Taurid swarm, through which the Earth periodically passes, changes the odds significantly. If their hypothesis is correct, the swarm heightens the possibility of a cluster of large impacts over a short period of time. The study's lead author, David Clark, together with colleagues from Western University, simulated a large collection of 100-meter diameter meteoroids, just like the one which triggered the Tunguska event, and placed them in orbits similar to the Taurid swarm, calculating their positions forward for 1,000 years. By analysing each object's position and motion over time, the authors calculated two optimal viewing times and telescope pointing locations for the Taurid swarm, in order to properly investigate its real overall risk potential. According to their data analysis, planet Earth will approach within 30 million kilometres of the centre of the Taurid swarm over the next few months, in what will be the closest such encounter since 1975. By the way, that 1975 swarm event hit the Moon, triggering the Apollo seismic sensors on the lunar surface. The calculations also show that this will be the best viewing time for the Taurid swarm until 2032. Clark says the results have triggered a great deal of interest at the recent Planetary Defense Conference in Washington, D.C. He says there's strong meteoritic and NEO evidence supporting the Taurid swarm and its potential existential risks. Dr. Aaron Cavosi from Curtin's School of Earth and Planetary Sciences says hazards from space remain a key focus for researchers because of the very real dangers they pose.
A lot of people think that planetary science on Earth and studying impact structures is kind of an academic pursuit. They're interesting, but, why should I care? Well, we still are very concerned about hazards from space. For anyone that needs an example of why one should be concerned about hazards, you can just look back to 2013 and that fireball that erupted over Chelyabinsk in Russia that caused all the damage and blew out windows and sent a lot of people to the hospital. That was an example of a meteor that never hit the ground. It blew up in the atmosphere. So that was kind of a small one. The events that make these impact structures that create holes in the ground that are 10 or 15 kilometers across, these are city killers. If they happen in a marine environment, they will cause tsunamis that will just be devastating in coastal environments. And so the only way that we can understand the frequency of these events occurring in the geological past is to do this difficult work to identify the impact crater record on Earth. Astronomers also shine their telescopes up to the sky and do surveys of space to count asteroids of various sizes that are orbiting and try to make predictions about what could hit us in the future. But the other half of that coin is understanding what has hit us in the past. And so there's a very real reason to continue to look for impact structures, and so we can characterize what the impact flux has been, meaning how often does Earth get smacked? We know the big one that took out the dinosaurs caused a major mass extinction. Geologically, that was only 65 million years ago. For most geologists, that's pretty much yesterday.
It's not really a case of could, but when will it happen again? Because it will happen again.
Absolutely. If you dial into NASA and other national space agencies, they spend billions of dollars per year monitoring so-called NEOs, or near-Earth objects, for this precise purpose. The impact structures that we're talking about are simply NEOs that made it through the atmosphere and caused a lot of damage and destruction on the ground. So airbursts themselves, like in Chelyabinsk or the one at Tunguska that exploded over Russia in the first part of the 20th century, these are events that are profound and damaging and catastrophic. But keep in mind, these rocks blew up in the atmosphere. They didn't hit the surface. If they were a little bit bigger and hit the surface, the damage is much more profound.
We spent an awful lot of time and effort to try and find funding for Rob McNaught to keep his program going out of ANU. We were unsuccessful, sadly. How big an impact does not having a proper Skywatch program in the Southern Hemisphere have on our ability to be forewarned of asteroids, meteors, comets, which could be on a collision course with the planet? I mean, that's half the planet that's not covered, isn't it?
One of the issues is the fact that there needs to be monitoring at all times. Different countries have different priorities in terms of what they see fit to fund. And so I'm not going to come down on one side or the other on that. There is monitoring that's going on I'm quite grateful for. Do I think there should be more monitoring? Absolutely. And the question is, what size of object do you choose to fund in order to do surveys? Because I think the recognition that objects much larger than, say, 100 meters in diameter or 500 meters in diameter are going to cause some pretty catastrophic events. But if objects on the order of between 50 to 100 meters in diameter hit urban environments, they're still going to cause a massive amount of damage. And so society has to wrestle with how much money do you want to spend in terms of prioritizing, looking for, and tracking smaller and smaller objects, because that's what's on the scale here. How much money do you spend versus what confidence level do you wish to know for the probability of small objects? There's a lot more of the smaller objects than there are the bigger objects. And so I think this is what that community wrestles with.
And we're also finding that a lot of those smaller objects are actually interior of the Earth's orbit around the sun, making it even more difficult to find them.
Correct. Some things we don't know that we can't see right now.
That's Aaron Cavosi from Curtin University's School of Earth and Planetary Sciences.